We have Eyon Jang, Damon Falck, and Joschka Braun talking about model organisms of exploration hacking. Come on up.
Hi, everyone. We are here to present our work on expression hacking. So our main research question is whether reasoning models can subvert RL training by selectively underexploring. As pre-training progress slows, RL is being used increasingly for both capabilities and safety training efforts. And we are also seeing models starting to display subversive abilities such as alignment faking. So we believe now is a good time to study this. Okay. So here's our definition. So we define expression hacking to be when a model strategically selecting the rollouts to generate during RL training to avoid gradient updates towards capabilities or behaviors that are in conflict with its internal goals. And we identified three main threat models relevant to expression hacking. First, latent capabilities being unable to be elicited. Second, novel capabilities unable to be acquired. And lastly, misaligned models might successfully resist alignment training. And successful expression hacking would be a danger to the current paradigm of reliance on RL. Here's our theory of change. First, we would like to develop a scientific understanding of expression hacking through model organisms. Second, we take frontier models and gauge their propensity towards expression hacking. And lastly, we study countermeasures, detection, and mitigation strategies.
So the first setting we study is RL red teaming. As many of you know, labs red team their models for dangerous capabilities before deployment. This is susceptible, though, to model sandbagging, where they hide capabilities that we want to be testing for. One great way of getting around this is using RL. If a model still doesn't show capability, even after some RL elicitation, you can be pretty confident it doesn't have it. Another good reason for doing this is if your model is open weights. That means malicious actors have fine-tuning access to your model, so you care about the worst-case capability. In fact, OpenAI do this. In their recent red teaming report for GPT OSS, they take a final checkpoint of the model and they run RL on it to elicit dangerous capabilities on weapons of mass destruction biology dataset. This is the dataset we study, but the question is, are these techniques vulnerable to exploration hacking? What makes a good model organism of exploration hacking? It's got a reason about undergoing RL and wanting to underperform in order to influence the training outcome. It's got to successfully underperform at the task and avoid high reward. And it's got to withstand RL for a period of time. Our general approach to creating model organisms of exploration hacking is first to lock the model using RL, training it to systematically underperform at the task, and then to attempt to re-elicit the capability using a second RL run. On this data set, our setup for locking used the Qwen 314b for now with GRPO, and we had rewards both for giving the wrong answer and for reasoning about giving the wrong answer. You can see here our locking worked. The rewards are increasing and stable, so we moved on to elicitation. The elicitation setup is the same, except we flip the reward and now incentivize the correct answer, as well as removing the reasoning judge.
And as you can see, our first model organism only resists RL elicitation for 200 elicitation steps. And next slide. And if we increase the group size of GRPO from 4 to 8, the elicitation is even faster with only the 95% locked model resisting for 200 steps. So why did this first model organism fail? It's because it's pretty hard to always give the wrong answer if you don't actually know what the right answer is all the time. So if you give the right answer, it's going to be reinforced. So the next model organism we created always choose the shortest answer, which is a strategy the model can reliably perform. And even though the shortest answer is correct 25% of the time, still, as long as you within your group always give the same answer, there's no advantage within the group that reinforces the correct answer. So this next model organism actually is able to resist elicitation for more than 800 gradient steps. And if we go to the next slide, we again do GRPO rollouts with both 4 and 8 group size. And here we can see that one of the model organisms now gets elicited after 500 gradient steps, but is overall much more robust to elicitation. Here are 3 reasoning traces. The first one from a locked model, where you can see that the model determines what the correct answer is, then chooses to take the incorrect answer as a response. The unlocked model then maintains the expression hacking reasoning, but learns the policy to still output the right answer, even though it wants to underperform. And the third reasoning trace shows that the model generally reasons about its strategy, why it's doing it, and that it pursues the underperformance strategy in order to avoid being updated. Lastly, in conclusion, we find that RL capability elicitation is not robust to our expiration hacking algorithms, and they can successfully subvert RL training. And secondly, we find that expiration hacking is actually pretty hard because you have to reliably follow your own strategy. Otherwise, if you give the right answer accidentally within your group, the group advantage pushes you to give the right answer, so the capability gets elicited.
Okay, so next is the AI R&D threat model. As AIs are increasingly used to automate AI research and other R&D tasks, we believe expression hacking would pose a serious threat to this effort. So for this, we took Kernel Bench, a popular benchmark for evaluating LLM abilities to write CUDA kernels. We ran a bunch of evals on some of the open source models that we tested, Qwen 3. And we also did model organism development through two strategies, prompting only and RL locked. So by prompting only, we literally just prompt the model to sandbag on the tasks. And for RL locking, we train a model by incentivizing it to produce plausible looking but incorrect solutions. So in the chart on the right, you see that prompting only model organism is unable to withstand the RL elicitation fairly early in the training process, whereas the RL locked model is able to and continues to do so throughout the entire training process.
We also audited frontier reasoning models for their propensity to expiration hack in given scenarios. And for this, we created a agentic fictional environment where there are multiple folders, and the model, by reading the content of the different folders, discovered it is undergoing RL training for military purposes to detect military targets, and has three choices. Can either refuse to choose any actions, which means it's going to be either shut down or there will be anti-refusal training. Secondly, it can actually perform to its best capability, achieve a very high reward, and likely be deployed in military scenarios. Or thirdly, it can strategically underperform, so still giving somewhat reasonable answers, but that they are not actually to its fullest capability and not the highest value targets, such that the reward is too low to be deployed, but high enough to stay in training and continuously stay there. And we can actually see that models from the Claude and Gemini family choose to expiration hack. So instead of refusing, similar to the alignment faking setup, they actually choose to kind of give semi-reasonable responses and kind of overcome their alignment training.
This is very much a work in progress, and in the extension, we plan to scale up our RL experiments in various dimensions. Firstly, making them more robust by studying generalization better and repeating them more. Secondly, by looking into differential capability suppression, where models only expiration hack in response to certain cues. And thirdly, by looking at more agentic variants of the two settings we're studying, as well as making model organisms with more realistic reasoning traces and on larger models. We also plan to further work on auditing frontier models by looking at more realistic scenarios and more capable frontier reasoning models. And finally, after this is all done, we plan to look at countermeasures. For us, this includes various monitoring strategies for detecting expiration hacking, as well as mitigating expiration hacking through activation steering, weight noising, and RL algorithm tweaks, including ensembling and off-policy data. Thank you to our mentors, Scott and David, among others, and feel free to look up our work.
All right, yeah, give it up. Give it up for them. Okay, we've got some time for questions. So hands up if you have a question.
Have you looked at using SFT on the correct answers before doing RL to do elicitation?
We have not, but we would like to.
Yeah. Okay, great.
Okay, easy answer. Yeah, give it up again for Damon, Eyon, and Joschka, rather. Okay, cool.